Welcome back to Students Teach Orgo. In this video we'll be talking about the Diels-Alder reaction, and I'm going to start off by talking about the mechanism. So the Diels-Alder reaction occurs between two reactants. We're going to call this first reactant the diene and the second reactant the dienophile. So we call this the diene, right, because it's an alkene, meaning there's a double bond and there's two of them. So that's where the prefix di is going to come from. And then the dienophile just means it's the molecule that likes the diene. And so I'll show the curved arrow mechanism here. It's going to be a concerted reaction, meaning that all of these arrows, all of these bonds are going to attack all at once. And so you can see in our product here, we are going to form this new sigma bond here and that new sigma bond there from what used to be this pi bond and what used to be this pi bond. And then that double bond just moves over. And so this is the main template for every single Diels-Alder reaction that you'll ever see. So an important note is that the Diels-Alder only occurs when the diene is in the S-cis conformation. And so I'm sure you guys have heard cis and trans before, usually in relation to like stereochemistry and the position of substituents across double bonds. But in this case it means something different, because this molecule right here and this molecule right here are the exact same molecule. The only difference is that we've rotated along that single bond there to get these two different conformations. Now, because the Diels-Alder can only occur when the diene is in the S-cis conformation, a molecule such as this, where the diene is locked into that S-cis conformation, will be very reactive. However, a molecule like this, where you're stuck in the S-trans, will not react at all in the Diels-Alder. So next I'm going to talk about how substituents on the diene and dienophile can change the reaction rate of the Diels-Alder. The reaction is going to go faster if there's an electron donating group on the diene, and it's also going to go faster if there's an electron withdrawing group on the dienophile. So really quickly here, I'm just going to review what an electron donating group and an electron withdrawing group, what they are. And so you can see this table very nicely summarizes some examples of different donating groups. Activating here means the same case as donating, and deactivating would be the same thing as withdrawing. So you can see that these would be some of your stronger donating groups, these would be some of your stronger deactivating groups or withdrawing groups. And just feel free to reference this table in the following problems if you're confused as to whether a group would be donating or withdrawing. So the Diels-Alder reaction, if you start looking at molecular orbital theory, is all about this movement of electrons from the HOMO, the highest occupied molecular orbital of the diene, to the LUMO, the lowest unoccupied molecular orbital of the dienophile. And so you can see if we don't have any substituents on the diene or any substituents on the dienophile, we have this very basic template Diels-Alder reaction here. It's going to proceed very, very slowly because there's a really large difference in energy. Here, like on the y-axis, you could say that like this is the energy of the orbitals. So because there's such a far distance in between these two, it's going to proceed very slowly. However, when you add the donating group, in this case that hydroxyl would act as a donating group on this diene, and a withdrawing group, this ketone would be a withdrawing group for the dienophile, you can see that, and I've tried to show this using these arrows going across, or like these dotted lines going across, the energy levels of the orbitals on the diene have increased, and the energy levels of the dienophile have decreased, making it a much shorter jump to get from the HOMO of the diene to the LUMO of the dienophile. And this will just make the reaction go much faster. So in summary, the key takeaway here, because sometimes tests will ask multiple choice questions about this, is that an electron donating group would raise the HOMO on the diene, and the electron withdrawing group would lower the LUMO on the dienophile. So we've got our first practice question here. Which Diels-Alder reaction would proceed the fastest? This is a bit of a tricky question, so take your time, look at it. Feel free to pause the video if you'd like. But I'm going to go on. The answer is going to be B, and it's a bit tricky. Why, right? You can see that both C and B both have esters as the functional group, right? Now, esters are a little bit weird because they can both be an electron withdrawing or an electron donating group depending on how the ester is attached, right? This oxygen right here has two lone pairs, and if whatever you're attached to is, right here, then the ester is going to act as a donating group. However, if you're attached on the other side, now this is a withdrawing group because that carbonyl can take electrons and put them up onto the oxygen. So B would proceed the fastest because we have the ester, the oxygen right here, the donating part facing the diene, and the withdrawing part facing that dienophile. Where over here you can see I've swapped that. So B would be the fastest, and the other answer choices, right? This is the one with no substituents, so that would be pretty slow. And here, this is a very strong withdrawing group on the diene and a donating group on the dienophile, so that's backwards. Next, I'm going to talk about the regioselectivity of the Diels-Alder reaction. On the slide here, I have two different products being formed from the same reactants following a Diels-Alder reaction. You can see that in both cases, it's the same diene and the same dienophile. I've just taken the dienophile and I've flipped it upside down for this reaction here on the bottom. But notice that it's two different products, right? Up here we've got a 1-2 relationship between the donating group and withdrawing group, and down here we've got this 1-3 relationship. So how do we figure out which one is the correct product formed in the Diels-Alder reaction? Because when you do Diels-Alder, there'll only be one of these that'll be the major product. And it turns out that it was the reaction on the top with the 1-2 relationship between the donating and withdrawing group, that's actually the correct product. That's the product that'll be formed if you perform this experiment. And to rationalize this, we can draw some resonance structures and explain why it goes that way, right? So using the lone pair on the donating group, we're going to follow these curved arrows here and give us a resonance structure that looks like this, with a plus charge on this oxygen and a carbon ion down here. And for the dienophile, we'll do something similar. We're going to push these electrons up onto the oxygen, give a negative charge here, and a carbocation down here. Now, just looking at those resonance structures, it may not be clear how that helps us determine the regioselectivity, but if we go on to the next slide here, you can see that when you line up the diene and dienophile, and these are those resonance structures that I just showed on the previous slide, I still got them over here, the correct regioselectivity comes from this arrangement of the negative charge and the plus charge being next to each other, and then this plus charge and this minus charge being next to each other. So as you've learned, I'm sure, in lots of other science courses, opposite charges attract. And so the reason why this is the correct regioselectivity is because you have these opposite charges aligning with each other. Now you can imagine if I flip this upside down, right, in the example that was wrong, now you've got this positive and positive that are close to each other, and this negative and negative that are close to each other, and that's just not favorable, not a favorable interaction. So that would be the incorrect product, the incorrect regioselectivity. So here's another practice question to test that concept. Which of the following reactions would display the correct regioselectivity, and in which one would the product be the actual major product of the Diels-Alder? So pause the video, try to figure that out. This is a very, very helpful question. All right, I'll go on and show you the answer here. The answer would be D, and here I'll explain that on the next slide. So why was D the only one that showed the correct regioselectivity? Over here, I've drawn resonance structures of the diene and dienophile, and you can see that it's a little bit different than the resonance structures I showed you before, right? Because this time, instead of having the electron donating group on this carbon, the electron donating group's on this carbon. And so the only good resonance structure we can draw puts the negative charge on this carbon, right? Instead of, if the ether had been here, the negative charge would have been all the way down here. And so then the other thing we can do is for the dienophile, we can take this double bond, move it here, take one of those pi bonds, put it on the nitrogen, and that gives us this guy. And so we're going to want to line up that negative charge with that positive charge, And now we have a 1,4 relationship between the electron donating group and electron withdrawing group. Alright, so we can summarize this by saying that if the electron donating group and electron withdrawing group are in a 1,2 positional relationship or a 1,4 relationship, then you've figured out the correct regioselectivity. But if you ever have the donating group and the withdrawing group in a 1,3 relationship, as these were all of the wrong answers from the previous problem, right? Here, that's the donating group, that's the withdrawing group. Sorry, that's 1,3. And anytime it's in a 1,3 positional relationship, that's the wrong regioselectivity. All right, the next step is to talk about the stereochemistry of the products in the Diels-Alder reaction. So here I've got an example of a diene and a dienophile coming together and reacting in a Diels-Alder reaction. And you can see here in this product, I've followed the correct rules for regioselectivity, right? This is the donating group, it's in the 1 position. This is the withdrawing group, it's in the 2 position. So the regiochemistry is right. But now we have to pay attention to stereochemistry. So the question I'm going to ask is how many stereocenters are found in this Diels-Alder product? Normally stereochemistry is something introduced in Orgo 1, so this is a good opportunity to just test your memory, make sure you remember the rules for identifying stereocenters. So it turns out that this product would have 4 different stereocenters, right? There's 4 different carbons that are sp3 hybridized and have 4 different substituents. So this is the same example from the previous slide, but in this case I've drawn the stereochemistry in the manner in which it's been observed to occur in the Diels-Alder reaction. So this is the correct stereochemistry. In this example, the Diels-Alder is actually going to produce a racemic mixture, meaning a 50-50 mixture of these 2 enantiomers, meaning mirror images. And you can see here that the reason why they're mirror images is that at a very single stereocenter, the stereochemistry is inverted between the 2 of them, right? So like this is wedged, dashed, so on. So I know this could look intimidating, like, oh, how do you determine, what the relationship between the wedged and dashed is, and it's a very confusing looking molecule, but there's some simple rules that will make determining the stereochemistry very easy. And so the first rule here is we're going to be focusing on the dienophile, right? On the dienophile, groups with a cis relationship will be cis in the product, and groups with a trans relationship will be trans. So what that means is that you can see here the electron withdrawing group and 3 have a cis relationship, right? They're on the same side of the double bond. And that means in the product, both the electron withdrawing group and 3 will both be wedged, right? That means they're on the same size, wedged or dashed, either or, it's arbitrary. And 1 and 2 are on the same side of the double bond, so they are cis, so they're both going to be dashed. And you can see that 2 and the electron withdrawing group have a trans relationship, so now they're also going to have a trans relationship by this one being wedged and this one being dashed in the product. So that's how you determine the stereochemistry with the dienophile. For the diene, it's going to be a little bit different. Groups in the cis position on the diene are going to be on the same side in the product, and groups in the trans position will be on the same side in the product. So this is an example of a diene, right? And I've labeled the 6 different positions in which a substituent could be attached to the diene. And it's a little bit confusing that they still use cis and trans to describe this, because I guess like this cis refers to the fact that this substituent is cis to the rest of the molecule over here. But these are just the terms that they use, right? So if you follow this little template here, you can see that if you have a substituent that is pointed away from the molecule, we call that the transposition. And another substituent down here that's also pointed away from the molecule in the transposition, that they're going to be on the same side in the product. And that pointing inwards here and pointing inwards here in these 2 cis positions, they are also going to be on the same side in the product. Now, you don't have to worry about meta because this isn't even a stereocenter, right? This is a double bond. So if there's a substituent in the meta position, it just stays there. But you can kind of see how these 2 substituents fold out, but they'll stay on the same side. So let's put those 2 rules together now, and this right here is your master template for determining stereochemistry in a Diels-Alder reaction. So you can see that for the most part I've just combined those last two figures I've shown you, except, this is very important, I want to show you that the electron withdrawing group is going to be on the same side of the molecule as the trans substituents. So if the electron withdrawing group is wedged, then the trans substituents also need to be wedged. If I had decided to make the electron withdrawing group dashed, the trans substituents would also have to be dashed. And so there's a cute little phrase that can be used to keep this rule in mind, right? The cis shall be trans and the trans shall be cis to the electron withdrawing group. So you can see the cis substituents are trans to the electron withdrawing group, and the trans substituents are cis, or on the same side as the electron withdrawing group. So to introduce these terms here, endo versus exo, what does that mean? Endo is when the electron withdrawing group is on the same side as the trans substituents. Exo is when the electron withdrawing group is on the same side as the cis substituents. Now, whenever you do a Diels-Alder reaction, the endo is always going to be the major product, and that's why the electron withdrawing group should be on the same side as the trans substituents. So here's our first practice problem for stereochemistry, right? Draw the major product of the following Diels-Alder reaction, include stereochemistry where necessary. If you think that you can do this question by yourself, go for it. But I'm gonna walk through this one step by step in the next few slides here. So the way that I would attack this problem, right, is the first thing I'd notice is that the diene is not in the S-cis conformation. And if it's not in the S-cis conformation, no reaction is going to happen. So I would just rotate it along the single bond to go like that. So you can see if I have this right here, right, and I kind of spin it like that, it's going to move up here, and now it's in the S-cis conformation. So that's the first thing I would do. Now the next thing I would do is I would move the Dienophile to line up with the diene in the way that the Diels-Alder reaction is going to occur. So you can see by moving this molecule over here now, we've positioned the molecules in the way that will make it just easier to follow what's going to happen in the Diels-Alder. So next I'm going to draw out the product, and you can see that, you know, I followed those arrows, right, from the template earlier, right? There's a new bond between here and here, a new bond between here and here. This methyl group is going to stick out, this methyl group is going to stick out, and that's going to give us this product right here. And so I would recommend just drawing the product first without thinking about the stereochemistry too much. But now we have to realize that that's a stereocenter, that's a stereocenter, that's a stereocenter, that's a stereocenter, and we have to figure out what the correct conformation is, whether they should be wedged or dashed. So this is the electron withdrawing group, right? Because it's an aldehyde. The electrons can go up here onto this oxygen. This is the donating group. It's an ester, but this oxygen is pointing towards the double bond here. So this is a donating group. So if we decided to make this wedged, then we can figure out the rest of the stereochemistry from there. But that should always be your first step, is just assign wedged or dashed, it doesn't matter. Just assign some sort of stereochemistry to the electron withdrawing group. Because once you do that, you can figure out the rest. This aldehyde is on the opposite side from this methyl group, which means that they have to have opposite stereochemistry in the product. So now we know that this is dashed. Then we can look at our exo versus endo rules. This methyl group right here is a trans substituent, which means the trans should be on the same side, the trans shall be cis, to the electron withdrawing group, meaning that this has to be wedged. And this methyl group is a cis substituent, and the cis shall be trans to the electron withdrawing group. So that means this has to be dashed. And so if you go on to the next slide here, you can see the correct answer has that stereochemistry that I was just talking about. Of course, there will be an enantiomer, right? So if you had decided to do the problem and you'd made this dashed and that wedged and that wedged and that dashed, that's the other enantiomer, and that would be correct as well. All right, here is the next problem. I'm going to let you guys pause the video, try this one yourself, and I'm not going to walk through this answer as much as I did last time. So pause the video. For this one, the answer is going to look something like this. This problem is a bit tougher because this is giving us a bicyclic compound now. Bicyclic meaning that, you know, it's three-dimensional. You got a bridge of carbons sticking out between the rings. So these are both the correct answer. I just drew one in like a planar view, like top down, and I drew the other one from a more three-dimensional view. But yeah, this would be the correct stereochemistry. You can see that this here, and the problem, right? These are the cis substituents, right? That's cis and that's cis. And this is our electron withdrawing group. It's got electron withdrawing group on both sides. But that means that the cis substituents are still going to be trans to the electron withdrawing group. And the reason why we know that this is trans, right, is because if these hydrogens are sticking up, that means this has to be dashed and that has to be dashed. And so you can see if this is going up, these guys are going down. So the cis is trans to the electron withdrawing group. All right, and so just to talk a bit more about endo versus exo, right? This is how the exo product would look, and you can see here that they've drawn in those dashes to more clearly show the stereochemistry. But remember, the endo is always going to be the major product. That's what we're looking for. All right, this is a bit of a side note. I didn't know exactly which section to put this in best, but it is important to mention that alkynes can also serve as the dienophile in the Diels-Alder reaction. So far we've only seen alkenes be the dienophile, but alkynes can be the dienophile too. It's the same arrows, right, as the template with an alkene, but now notice that you're going to have two double bonds in that six-membered ring that's formed. What is nice about alkynes being dienophiles is that now you don't have to worry because there's no stereochemistry here and here. You just have to pay attention to whether this substituent and this substituent are both in the trans position or both in the cis position. But it works very, very similarly. All right, only two more sections to talk about here. So it can happen that the diene and dienophile are on the same molecule. And when we have a Diels-Alder reaction, when it's all part of the same molecule, we're going to call it an intramolecular Diels-Alder reaction. Now, an intramolecular Diels-Alder can create two rings, right? So you can see in this example here, this would be a new bond formed, this would be a new bond formed. This whole thing is going to wrap up over here, right? The molecule is going to rotate, so that way when the Diels-Alder occurs, it's going to create the six-membered ring that we're used to seeing, but these bridge carbons in the middle here are going to form this second ring on the side. So I've got another practice question for it here, and I'll take it slow and walk through this step by step. But let's try to find the major product of this intramolecular Diels-Alder reaction, and we'll pay attention to stereochemistry as well. So if I were to be the one solving this problem, right, my first thing that I would do is get this into the S-cis conformation, right? Because right now this is not in the S-cis conformation, this isn't the reactive conformation. So just by switching, by rotating that single bond like that, we can now put this into the S-cis conformation. So that's step one. Step two is I want to draw the dienophile, and I want to put that dienophile over here, right? Because that's where it's going to react with the diene. So temporarily, right, I'm just going to draw the dienophile and the diene just like this. I know there's some carbons attached here and some carbons attached here, but let's just line them up this way, right? Now, we know that there's 1, 2, 3, 4 carbons in between the diene and the dienophile. So that means there has to be 4 carbons here, like 1, 2, 3, 4, something like that. So if I go into the next slide, I'm going to draw it really ugly, but that's okay. So there's our 4 carbons that I know bridge between the diene and dienophile. So after I draw ugly like that, I'm just going to clean it up a little bit. So now we know that it's probably going to make 2 six-membered rings based on the fact that there's 4 carbons in this bridge here. Now we'll actually go through the arrow pushing and actually, go through the Diels-Alder, right? So that, that attacks there, that moves over here, and we'll get this as the product. Now we're really close to being done, but we just have to fill in stereochemistry, right? There will be stereochemistry at this position and this position, technically this position too, but it's not super programmable. So I know at least for when I was taking Orgo 2, they didn't have you didn't have to explicitly show the stereochemistry at that position, even though there is. Now here's the tricky part, right? So this electron withdrawing group is on the same side as the rest of this bridge over here, which means that if we decided to make this wedged, right, I'm just going to choose that arbitrarily, this should also be wedged. But we generally don't draw the wedge in the ring like that, so instead we'll just denote it by making a dashed hydrogen. Because if this hydrogen is dashed, that means this has to be wedged. And that's all the stereochemistry we need to worry about. So that right there will be our answer. And so again, I've just drawn the answer down here with the carbons numbered, just so that way it might be easier to follow which carbon ends up where in the product. Here is another practice question for an intramolecular Diels-Alder. This one is a little bit trickier, a little bit more things to keep track of. I'm not going to walk through this one, so pause the video and try it yourself. And here, I'll show you the answer. This would be one of the enantiomers, right? So if you switched around the stereochemistry, that's okay. But this would be the correct answer here. You can see that this is your diene. This right here is your dienophile. This is going to wrap around over here. This oxygen would be in the cis position, so it should be on the opposite side of the electron withdrawing group, and that's exactly what we see here, right? The oxygen is wedged, the electron withdrawing group is dashed, so the cis shall be trans to the electron withdrawing group, and then, you know, this the electron withdrawing group is on the opposite side now to the rest of the molecule, so if the electron withdrawing group is dashed here, that means this should be wedged, and we denote that being wedged by putting that dashed hydrogen. So this is just another, I think, helpful figure, right? If in an intramolecular Diels-Alder, if this molecule is linked through the terminus of the diene, you're going to have a planar ring, right? It's going to be two-dimensional. But if you have it linked through here, that's when you can get the weird bridged bicyclic compounds. So that's just something to keep an eye out for. Sometimes I think it's harder to do these questions with the bridged bicyclic ring because the 3 dimensions get a little funky. Alright, and in the last section, I'm going to mention the retro Diels-Alder reaction. So everything we've been looking at so far in this video can sometimes also be reversible. So you can see that, you know, it's the exact same template I showed you in the first slide, just the other direction now, right? So you've got the 6-membered ring, the alkene, reverting back to a diene and dienophile. And if you're interested to see what those arrows would look like, right, that bond, that sigma bond would now make a pi bond over here, that pi bond would move over, and that sigma bond would make a pi bond there. And so I think the best way to probably learn more about this is just to do another practice question. And this is going to be a little bit different than the questions before, because now I want to see if you guys can try to draw out a curved arrow mechanism to show the transformation of this molecule here on the left to the one on the right. And this is very tricky, so I'm going to give you a hint. There's going to be a retro Diels-Alder, and then we're going to follow that with a regular Diels-Alder. And yeah, try to pause the video. This is a tough question, but it's a good example for the kind of question you might see as like the 10-point question on an exam. Alright, I'm going to go through and show you the answer. So we're going to start off with that retro Diels-Alder, following the arrow mechanism that I just showed you 2 slides back now. So by following those arrows, we're going to lead to 2 products now, right? Because we broke that sigma bond and we broke that sigma bond. And so now these 5 carbons right here are going to be these 5 carbons right here, and this bunch of atoms over here is going to become this molecule, right? So we cut right through there. Now we know that we had to cut there because of this double bond, right? So if in our normal template, you know, this plus this comes together to make this, we know that this bond and this bond were the ones made, so those are the ones that we're going to break going backwards. Now to get from here to here, I'm just going to redraw these and just rotate them a little bit. So I'm gonna rotate them like that. And now you can see that we can just proceed forward regularly with the Diels-Alder that we've been seeing all day, and this would be an intermolecular because it's between 2 molecules. And so if you draw arrows to do another Diels-Alder, that'll give you the products right there. So that will be all for this video. I hope it was helpful, and now you know a thing or two about the Diels-Alder reaction.